Now, let's look at this special case when m is equal to minus 1. That is, we want to find the integral of x to the power of minus 1 dx. Recall that x to the minus 1 is the same as 1 over x. So this is equal to 1 over x dx. How do we find this special case? Well, we should begin by recalling a result from differentiation. If I set capital F equal to log x, where here log x, ln, means natural logarithm. Okay. Hopefully you remember from differentiation that the derivative of log x is 1 over x. So f prime equals 1 over x. And now I can use the fact that integration is the inverse of differentiation to write the indefinite integral of 1 over x is equal to log of x plus c. Now there's one caveat here. Log of x is only defined when x is greater than 0. So I should add here, this result is for x greater than 0. But in a moment we'll derive the general result. So, a moment ago we derived a result for the case when x is greater than 0. When x is greater than 0, the integral of 1 over x dx, which I can write like this, and you'll sometimes see written that way, is equal to the natural logarithm of x plus c. But what about the case when x is negative? Well, we can repeat the argument, just modifying it slightly, and it goes as follows. Let now f equal the logarithm of minus x. And this will be well defined because x is negative, so this argument is positive. Then let's make a simple substitution. Let u equal minus x, so f is log of u. Then we can apply the chain rule to find df by dx. df by dx is equal to du by dx, df by du. And du by dx is simple, that's just minus 1. And df by du is also simple, it's just 1 over u. Remember that 1 over u is the same as 1 over minus x. So the minus signs cancel out here and we're back again to 1 over x. That's fortunate because this is what we're seeking to integrate over here. So using the fact that integration is the inverse of differentiation, I can go straight away to the fact that the integral of 1 over x is given by log of minus x in this case. So there it is. It has the same form, but with a minus sign now here. Well, I can combine these two results simply by writing log of the absolute value of x. The absolute value means take the value and make it positive. And that's what we have here. Let's continue exploring this idea that integration is the inverse of differentiation. And this time we'll take a simple example where capital F is a trigonometric function, in this case sine of nx. Here n is just a constant, so I can calculate the derivative of f by bringing out the constant and then turning the sine into a cosine. And if you don't believe me, you can check this by using the chain rule we saw in the last clip. Now, here's the derivative of f, and straight away I can use this result, put that into here, and I have that the integral, the indefinite integral of n cos nx dx is equal to sine nx plus c. Okay, that's good, but even better would be to take the n to the other side. That is, first pull out n as a constant and then divide through. So I'm going to write this as the indefinite integral of cos nx with respect to x is equal to 1 over n sine nx plus c. Now, again, I should technically divide the c by n, but since c is just a constant whose value we don't know, I'm just going to leave it as c. Okay. That's the result for cos. We can write down in a very similar manner the result for sine. Excuse my handwriting. But this time we need to remember that when we take the derivative of a cos, we bring in a minus sign here. So there'll be an additional minus sign in the relationship. That's just one thing to watch out for. And there we have it, simple. Now let's look at an example of a trigonometric function which is more difficult to integrate. The case of the integral of sine squared x dx. Here this notation means the square of sine x, and it's just a quirk that we write the power here rather than putting the brackets and writing it here. It makes it quicker to write. So what is the integral of sine squared x? Well, using the idea that integration is the inverse of differentiation, we have to find some function whose derivative gives sine squared x. But off the top of my head, I can't think of that function. So fortunately, there is a method for leading us to the right answer. And that method makes use of a double angle formula. You might not recall, but the double angle formula for cosine of 2x is cos squared x minus sine squared x. Another way to write that is 1 take 2 sine squared x. Well, how do I go from this line to this line? Here I'm using the fact that sine squared plus cos squared equals 1. Excuse my abbreviation. So I put that in here to get down to here. Or rather, I've written this as cos squared equals 1 minus sine squared and substituted in there. Now, we can do a little bit of rearrangement to make sine squared the subject of the equation. Sine squared of x will, once we've rearranged, equal half of 1 take cos 2x. So we've rewritten the integrand and we can put that in here. But why have we gone to this effort? Well, we know how to integrate cosine of 2x. We did that in the previous clip. And we also know how to integrate a constant. Let's see that in action. I put this in here. I'll bring out the factor of a half. And then I have the integral of 1 minus cosine 2x in brackets dx. We should never forget to add the measure of integration. Now I can integrate each of these terms separately, so the 1 will integrate up to x. This is just an example of the first result which we derived. So I've got a half times x from integrating this, and this term will go to a half sine 2x using the previous video clip result. But one way to check this is to try going backwards. If we differentiate this, do we get back to this? So the x differentiated gives 1, and the minus half sine 2x gives minus cos 2x. Why is that? We bring out the 2, that cancels the half, and the sine goes to a cosine. So everything's working here. Just one thing I've forgotten, the constant of integration. And there it is, a result which is not immediately obvious, but by combining two results, a double angle formula and this idea, we've come to the right answer. With this simple idea that integration is the inverse of differentiation, you should now be able to integrate some simple functions. For example, x to the power, e to the nx, give this one a try, 1 over x plus a constant, give this a try, and then some trigonometric functions. For example, sec squared x, you can integrate this if you think about what differentiates to give this result. On the other hand, there's some functions which we don't yet know enough to be able to integrate. For example, tan x or e to the x sine x. In the next section of the courses, we'll be learning some hints and tips for these kind of functions. And then there's a borderline case, 1 over x plus 3 times x minus 2, which you might be able to integrate if you give it some thought. So why not have a try?